So this is the third exam review session. During this session, we are going to go over just any of you guys' concerns, questions about anything regarding this unit's topics. So we can address stuff from online homework, written homework, whatever you want. Quizzes too are especially important. So if you have questions about that, feel free to ask too. And then we can just go over general topics too. Like if you're just not sure about a specific topic in general, we can address that as well. But usually it's better to kind of explain things in the context of a specific problem, which is probably the best way to kind of think about things. But with that being said, first off, we had our quest to go over the last problem on the practice exam that the professors gave you. So if you're pulling the exam off of my Google Drive, that would just be the exam labeled practice exam. Not extra practice exam 1, not extra practice exam 2, just the regular practice exam. It's problem 8, Kirchhoff's rules, right? And it says the picture shows a circuit with 1 battery and 4 resistors. Let me write down problem 8. We have this circuit here, right? We have a nice little battery with an electric potential voltage. We have a resistor over here. We have some resistors over here as well, right? And then a resistor over there. So this is R1, R2, R3, and R4 that they've labeled for us, right? So they have R1 as being 4 ohms for its resistance, R2 as being 2 ohms for its resistance, R3 being 4 ohms for its resistance, and R4 being 3 ohms for its resistance, okay? So resistance is measured in ohms once again. Now, just to try and briefly rehash what I've been saying the past 2 days about circuits, the analogy that I had set up, that I came up with for thinking about circuits, is to think about things as a tree, right? So you can think about the battery as being the roots of a tree, supplying nutrients, supplying that electrical potential, that voltage, right? So if we draw a tree like this, we have the roots here providing the voltage, that's your battery, and then the trunk and all the different branches are going to be the wires, right? And then along those wires, right, there's not really room, I guess, for resistors in this analogy, but just think about the resistors being along the tree trunk and the branches and stuff somewhere, right? Now the idea here is that as you go up this trunk and as you go through different branches, you're going to be experiencing or encountering different resistors. So as you go up the trunk, right, you might have a branch that goes like this. This is a normal branch, right? This is just a regular old branch, no extra branches coming off of it, right? So if we were to think about this, here is the battery, this is your voltage, right? You go through and you hit a resistor, right? So I go through and I hit a resistor, right, on this branch here. That's my R1, right? Now, if R1, let's say we forgot about all this here, right? If R1 came back through here, right, no extra branching off, right? No other branches, no other resistors encountered, then that resistor is perfectly in series with the battery. It's consecutive, right? So the idea of something being in series with something else means that it's consecutive, right? It's continuous, right? So you can think about, this is another analogy as well, like a TV series has consecutive continuous episodes. We go from one episode to the next, from the trunk to the branch in a continuous, seamless, consecutive manner, right? So there's no extra branching off or anything like that. And when I mean branching off, I mean branching off or splitting off of the current, right? So the current is defined as some charge, right, that's being delivered over a specific unit of time. And so the idea here is that this charge goes through the wire that's delivered from the battery, and it passes through these different resistors. And as it passes through, it could just simply pass through, no problems, no issues, or it could get split off, right? It can get split off into what are called junctions, or how I like to call them, branching points, right? So these branching points are not just here, right? Because this is a normal branch. This is a regular branch that's in series with the rest of the trunk, right? It's consecutive, it's seamless with the rest of the trunk. But you could also have, and this is more common, right, where you have a tree like this with a branch that has branches of its own, right? Has branches of its own. So we could say, for example, that this is R1. Here's our main branch, right? And now we have sub-branches. We have this branching point here where the current, right? Let's say if this is water coming up, there's nutrients coming up from the roots, right? This is our current, this is our charge. As it's being delivered to the rest of the tree, right? It goes past that R1, past that resistor 1, right? But it can branch off now into different resistors, into sub-branches, right? At this junction point, at this branching point, right? So if you want to relate this now to the rest of the circuit, right, with the resistors and everything, up to here is our trunk, here we hit our branch, and now here is this junction, this branching point, which is point B on the diagram. That branching point is effectively this junction, and that's where the current will split off, right? That's where maybe the nutrients, the water, are going to go up to different resistors, are going to go up to different points, are going to go up to different branches, right? So this is what I like to call a branching point. Formally, it's called a junction, right? Formally, in the physics terms, it's called a junction. I like to refer to it as a branching point, because then I can think about this branch, right, sub-branch 1 and sub-branch 2, right, as being these little branches here, right? So I have, let me choose a laser here. So this would be like sub-branch 1, right? And then this entire piece would be sub-branch 2, right? So my current, let's say I deliver 3 amps, right, from the battery. 3 amps goes through here, still 3 amps. Now it hits this branching point where it can go into different sub-branches. Maybe 2 amps is delivered up down here, and 1 amp is delivered up there, right? And the idea here is that this is an input kind of branch, right? This is an input point, and then you have another output point, which is E label on the graph, right? And so at this output point, the current must, quote unquote, reunite, right? So it has to go from, all right, we split off into 2 amps and 1 amp here. Now it has to reunite to 3 amps here. So the current, the charge has to be conserved, right, after you go through those branches, right? So that's the idea of how to think about whether things are in parallel with one another or series with one another, right? When you hit this branching point, whatever branches come off of it, those branches are going to be in parallel with one another, right? So I have this trunk, I have the R1 going through here, everything up to here is in series, right? But now we hit this branching point. After we hit this branching point, anything coming off of this branching point, those branches or sub-branches are going to be in parallel with one another, right? So I can say now that this branch and this branch, they are in parallel with one another. Now, what's unique about situations like these where you don't have just one resistor here and you don't have just one resistor there, you have more than one resistor on one branch, right? The idea here now is that we have to recognize, once again, we defined series resistors as resistors, or you could say the same for capacitors as well. The same concept applies. Where you have a series resistor or a series capacitor, that means that they are connected consecutively, continuously, with no extra separation, splitting off, branching off of the current anywhere in between them, right? So we had 3 amps delivered, for example, right? So we went in, 2 amps got delivered here, 1 amp got delivered there, right? So as this 1 amp is traveling through this branch, it's continuous. It's going from R2 to R3 without any extra branching points or splitting off of the current anywhere else, right? So 1 amp goes through here, continues, and its output here, and it reunites with the 2 amps from up there, right? So because there's no extra splitting off of the current or branching off of the current in between R2 and R3, can someone tell me what R2 and R3 would be considered? What's the relationship between them? They are in series. Perfect. So these would be in series. And then, right, the idea of simplifying a circuit down is that you want to have everything in series with everything else, right? We want one big combined or pseudo-combined resistor at the very end that is going to be just a combination of all the resistors, and then that combined resistor is going to be in series. It's going to be continuous with the battery, right? That's the goal at the end, is to get basically just one mega resistor that has everything included in it, right? So if we wanted to define what this mega resistor would be, right, it would be labeled R1, 2, 3, 4, right? That would be the resistor for the entire system, where you include R1, R2, R3, and R4, right? R1, 2, 3, 4 is the equivalent resistor, the pseudo-combined resistor for this entire system, right? Now, how do we get this resistor simplified like this? Well, we trace our current, first of all, right? And as we experience these branching points, we simplify things down, right? So, four resistors in series, you can add up the resistors very simply, right? Resistors in series, you can just say whatever resistors you have, like R1 plus R2, right? Plus R3, etc. You add them up like that, that's perfect, and then you get your equivalent resistors. So this is in series. For parallel, what you have to do is you add up the reciprocals of the resistors, right? So if you had R1, you'd add 1 over R1. If you had R2, you'd add up 1 over R2 as well, 1 over R3, etc., right? And then you get 1 over the equivalent resistance in parallel. So if I added all of this up, like if I had, let's say I had 2 resistors in parallel like this, right? This is 2 ohms, and this is 3 ohms, right? It would be 1 over 2 plus 1 over 3. And then whatever sum I get from that, right? So if I had 1 over 2 plus 1 over 3, right? This is 3/6. This is 2/6. This is 5/6, right? And so 5/6 is only equal to 1 over the equivalent parallel resistance. So you just have to flip it. You just make it 6/5. And that's your RP, right? That's it. So that's how to look at parallel and series resistors and how to simplify them. Now, there's a couple rules that you have to keep in mind as well, right? A couple rules you have to keep in mind. So for series resistors, you have charge / current must be the same across them, right? There must be no branching off of the current, no splitting off of the current. The current must be completely conserved between resistors that are in series with each other, right? So the charge or the current must be the same, right? The resistance, we said we can add it up like that. And then we add up the voltage drops, right? So add up voltages. So across every resistor that you encounter, it's going to drop a certain amount of voltage from the voltage that was delivered by the battery. So if we have 24 volts at the start of this, right? If you go through this resistor right here, R1, it's going to cause the voltage to drop by a little bit, right? You go through other resistors, it's going to drop the voltage by a little bit more, right? Now, between resistors in series, right, you just add up the voltage drops between them to figure out the total voltage drop, right? Because eventually, when you go from 24 volts to maybe you dropped 12 volts, to maybe you dropped 6 volts, 3 volts, whatever, until you finally get to 0 volts. And then that 0 volts, once you've gone through all of the resistors, right, you effectively have dropped the voltage completely, and then you kind of go back and recharge, right? So it's kind of like, okay, I start off with 24 volts here, I dropped some at R1, I go through R2, R3, and R4. Now, by the time I've gone through that parallel branch, I effectively have 0 volts, and then when I go back through the battery, it's like recharging it almost, right? That's kind of an informal sense, but it's kind of like recharging the voltage again, right? So for parallel resistors then, the charge adds up between parallel resistors. Why? Because we already said that the current is splitting off, right? So like I said earlier, if we came in with 3 amps, 2 went up here, 1 went down there. So these have to add up, right? So the current between branches have to add up to the current that came in before the branch. And it has to add up to the current that comes after the branch, right? Because there's an input and output point. Whatever comes in must come out, right? So 3 amps came in, 3 amps must come out, right? So the energy, or not the energy, the energy too, but the charge and the what's it called? The current must be conserved with each other, right? So as you go through these branches, the current will add up between the different branches. Now, once again, we said that the equivalent resistance in parallel is just adding up the reciprocals, so 1 over R1 plus 1 over R2 plus 1 over R3, right? And then finally, what's unique about the voltages for resistors in parallel is that the voltage between branches that are in parallel is the exact same, right? The voltage between branches in parallel is the exact same. So, for example, if I had 24 volts here, let's say 12 volts is dropped there. How many volts do I have left to go through those two branches? 12 volts, right? I have 12 volts left, right? 12 volts is not split up between the branches like the current is. So I can't just say like, oh, I have 8 volts going through here and I have 4 volts going through there. No. It's 12 volts going through here and 12 volts still going through there. Why is that the case? Because the idea is, once again, when I am doing a circuit problem, the goal is to simplify everything down to be in series, right? So if I were to simplify this whole thing down to some pseudo-combined resistor called R234, right? Where I combine everything in this branch here, these two branches, I combine them into one resistor, R234, then when that resistor R234 is connected to R1, they're going to be in series. They're going to be consecutive. They're going to be continuous. There's not going to be branching off between R1 and that combined resistor R234. And so if that's the case, well, if I go from R1 to R234, right, I just dropped 12 volts. So I have 12 volts left for this combined resistor, right? So that means that through the combined thing, 12 volts must be going through each branch, right? And that's kind of an informal sense, but also you have to realize that because they have the same input and output point, right? Because they come in at the same connection and they come out with the same connection, they're effectively, in that sense, one big resistor. And then, like I said, if it's one big resistor connected to each other with the same input and the same output point, then the voltage drop has to be the same across every single branch, right? So even if I had another branch here or another branch there, right, it's 12 volts here, 12 volts here, 12 volts there, right? And figuring out how much like voltage I have left is easy because, well, I don't want to say easy, but it's easy to figure out by looking at the other resistors in the system, right? So just look at resistors that would be in series with the battery, right? So I have this voltage from the battery here. R1 is in series with the battery because it's continuous. The current isn't splitting off between them. So now I'm like, okay, well, 12 volts just dropped off at this resistor, right? So I have 12 volts left. Oh, I have a branching point? Okay, cool. Well then, through these branches, I must have that extra 12 volts to where then after coming out of those branches, I have 0 volts. You might be asking, well, all right, what if I have another resistor over here, right? Well, in that case, if it's not a simple system like that, then I would recommend solving the entire thing first, right? Simplifying everything down, right? You simplify this branch. Once you have a combined resistor, you'll have R234, R234, R1, and let's say like R5 would be in series with one another. You can add them up, and then you figure out the current, right? Once you have the current, you can say, okay, voltage drop here was a certain amount. R5, since it's in series with the battery, there's no splitting off between the battery and R5. You can also find the voltage drop here. So let's say maybe 6 volts dropped here, 5 volts dropped there. That's 11, right? So now I have 13 volts left. 13 volts must go through here, 13 volts must go through there, right? It doesn't split off. Only the current splits off in a parallel branch. But the voltage must remain the same across every single parallel branch. So voltage stays same. So if we go ahead and start solving this, right, determine the equivalent resistance of the entire circuit. So now that I've kind of explained everything, right, hopefully you guys should be able to, walk through this with me. I don't want to like keep talking about this resistor stuff. I want to give you a chance to be able to solve it on your own. So one last thing I'll recommend is that as you simplify things down, as soon as you simplify like a parallel branch, right, immediately go back, start at your battery, right? So, I simplified all these 3 resistors into R2, 3, 4, right? I don't continue. Let me go back and start at the battery again so I can retrace my steps and figure out, right? Because you could have more than one parallel branch that you have to simplify. As you simplify parallel branches, restart at the battery and then retrace your steps through the circuit. Simplify another parallel branch, retrace your steps, go through the circuit again until you have everything in series, and then you can simplify at the very end. That's my last recommendation there for these problems. So if I'm determining the equivalent resistance of the entire circuit here, right, what can I start with? What do I do first? Exactly, right? So I want to look at R2 and 3 and 4 first. Why? Because the goal, once again, is to simplify everything down to be in series. R1 is in series? Check, right? Well, after I go past R1, I meet that branching point at point B. So now I have R2, 3 in one branch and R4 in another branch, right? Okay, well, now that I've hit this branching point, right, I have R2 and R3 in branch 1, right, or sub-branch 1, and R4 in sub-branch 2. Which resistors are in parallel with each other? What can you say properly about which resistors are in parallel with one another? Yes, so R2 and 3, they are in parallel with R4. I can't just say R2 is parallel with R4 or R3 is parallel with R4. That combined branch right there, right, between R2 and 3, R2 and R3 would be parallel with R4. Excellent, right? So R2 and R3 are parallel with R4. Excellent, right? Cool. Well, what do you notice about R2 and R3? Exactly. Excellent, Matthew. So R2 and R3 must be combined in series first before being parallel with R4. Excellent, right? So R2 and R3, once again, if you were to trace the current between them, there's no splitting off of the current between them, right? So those are in series. So those are easy to kind of add up, right? Because R2, 3, that would be the combined resistor of R2 and R3. That would be just simply 2 ohms plus 4 ohms is equal to 6 ohms, right? Well, now that we have R2, 3 and R4, we already said that R2, 3 and R4, they are parallel with one another. How can I simplify that down? Excellent. 1 over R2, 3 plus 1 over R4 gives us, what do we call that combined resistor at that point? Exactly. R2, 3, 4. And that's the equivalent resistance yet. So R2, 3, 4, right? So we have, what is it? 1 over 6 ohms, right? Plus 1 over, 3 ohms, right? So this is just 3 over 6, right? And are we done here? Exactly, right? So we take the reciprocal now. So we just flip this. So this is 6 over 3, and that's equal to R2, 3, 4. And 6 over 3 is just 2. So the resistance of R2, 3, 4 is 2 ohms, right? So now we've simplified the circuit down to this, right? We have simplified it down effectively now to R2, 3, 4, right? Excellent. Like I said, as soon as you simplify something down, then you start back at the battery. You move through it. Oh, I passed through R1. Excellent. Do I see any branching? No. I continue. Any branching? No. Continue. Oh, R2, 3, 4. Cool. Any branching? Continue. Any branching? Continue. Any branching? Continue. Oh, awesome. Done. No more branching, right? Everything's in series with each other and with the battery. So now that everything is in series, we just got to simplify it down to one big pseudo combined resistor, right? So how would we do that? What would we do? What's the next step? Now that we have R1 and we have R234. Exactly. So R1 plus R234. And what's that combined resistor called now? Exactly. R1234, right? So R1 is 4 ohms, R234 was 2 ohms, and now this whole thing is just equal to 6 ohms. Boom, done. That's part A. Right? Now, part B says the current through the resistor R4 is known to be I4 is equal to 4 amps, right? So I4 is equal to 4 amps. That's the current going through resistor 4, right? Well, resistor 4, what did we define it as, right? We said it was a branch, right? So if 4 amps is going through resistor 4, is that the full amount of amps that is going, like that was released by the battery? No, right? It's only part of it. It's only a branch of it. It's only splitting off from the original current, right? How can we find out what the total amount of current was that was being delivered from the battery? V equals IR, right? So V battery, right? Let's say, how do I want to say this? I could say, like, honestly, I can just say I battery or I total. Yeah, I can say I total. And then times R1, 2, 3, and 4, right? Because that would be the total resistance here, right? So that is how you would figure out, right? Normally. But what we haven't accounted for is the fact that, well, they haven't even given us a voltage of the battery, right? So that's unfortunate. That is unfortunate. Now, if you were given the voltage of the battery, right, you could find out the total amount of current, right? And then once you have the total amount of current, now we can look at what part B says. It says use the loop rule to determine the current through I2, right? Well, if we solve this out, right, let's say it was 24 volts and we're using the 6 ohms from before, right? So this is I total. So this is 6 ohms, right? So this doesn't work out. All right, let me do 48 volts instead. So 48 volts, 6 ohms for the total resistance of the circuit. So now we have I total is equal to 8 amps, right? So that's the total amount of current that's being delivered. So if I go up here again, right, I know 8 amps is being delivered by the battery. 8 amps because it's in series for R1 here. R1 is in series with the battery. 8 amps goes through here. That's fine, right? Now, let me actually go back and adjust this to be parallel again, right? So I have R4 and R2 and R3, right? Now, as the current kind of goes through here, I have 8 amps. It hits a branching point, right? They told me that 4 amps is going through here, right? 4 amps goes through here. Then, how many amps would go through the second branch? If the current is supposed to be splitting off, and the branches are supposed to be adding up the current, right? So the current is supposed to be adding up between the branches. How much would go through here? If I had 8 amps, and this was 4 up here, 4, yep. So 4 amps as well, right? And then 4 amps goes through R2, and that would be the amount of current that would be going through I2, right? Or R2, right? So we can say I2 is 4 amps as well. So that's if we were given the voltage, but that's not the case here, right? So instead we have to refer to something called Kirchhoff's loop rule, right? So let's see here. So use the loop rule to determine the current I2. Be explicit about your choice of loop, right? So let's see here. We have I4 is 4 amps, right? Okay. I see. Okay. So for this, what we want to do is, okay, hold up. All right, so essentially we want to go through and pick one loop, right? And by loop, we just mean like going through from positive terminal to negative terminal, right? So you just pick a loop, basically, right? So through any one of these loops, right? Through any one of the loops, we have to have perfect voltage drop. So like if we have 24 volts as we go through R1 and then R2 and R3, we'd end up with 0 volts here, and then effectively like that gets quote unquote recharged at the end, right? So we could also pick this loop where it's just R1 and R4, right? Just R1 and R4, that could be another loop. But as long as whatever like loop we pick, we have to have that perfect voltage drop between them. Or between that loop, right? Or within that loop, I mean. So let's see here. If we started out with, we know that effectively like normally we'd say like V battery, right? If we picked the big loop which is just R1 and R4, right? Then we know that V battery minus I1 times R1 minus I4 times R4, right? Because these would be like voltage drops, right? They decrease the voltage, right? And then by the time I go through that loop, I have 0 as my voltage here, right? So, what I want to, okay, so how do I want to word this? Okay, so let me adjust this. Instead of just saying it equals 0 at the end, let's say that the change in voltage, right? Change in voltage is 0, because that's what the loop rule technically is, that you don't have any change in voltage by the time you get to the end. So, like, what I'm trying to say is that here you have 24 volts, right? If you added up R1 and R4, the voltage drops between them, that should also be 24 volts, right? So this is like your VI, this is like your VF, essentially, right? So you start off with 24 volts, you end up with a voltage drop of 24 volts as well. So I guess if we define it in that sense, right, where we have delta V is equal to 0, then let's just look at I1, R1, and then plus I4, R4, right? And then that should just be equal to 0, technically, right? So I1, R1, but that would give you a neg, that's weird, hold up. All right, I'm doing something wrong here. One sec. Okay. Use the loop rule to determine the current I2. So for the loop rule, it's supposed to be telling you that the change in the voltage is supposed to be 0, right? That's what it is formally for that loop rule. But I'm trying to figure out, like, Yeah, that's just the expression for the loop rule. But I don't know what's throwing me off. I think I'm just messing up like my signs. Yeah, I mean, hmm. Oh, hold up. Okay, so, all right, I had that written at the beginning, V battery, and then minus, and we can just pick a loop. So I had I1, R1, and then I4, R4, right? Hmm. Yeah, that's what I had at first, and then that should all equal to 0. But the problem is we don't know what the batteries. Oh, hold up. So we had R234, R1234 was 6 ohms. Okay. So if we pick that loop, right, then really I1 should just be equal to I4, I believe, because then they would be in series, no? So I1 is equal to I4, I guess, by that. Okay, so V battery is just equal to, was a minus 4 amps, and then times resistor 1, which is 4 ohms, and then minus I4, which is 4 amps, and resistor 4, which was 3 ohms. And that's equal to 0. So V battery would just be equal to like 16 volts in that case, plus 12 volts, so 28 volts in that case for V battery, right? And then if we kind of redid the expression to factor in that second loop, right? So V battery, right, which is 28 volts now, and then we did the second loop, which is R1, R2, and then R3, right? So at that point, it would be minus I1, R1, minus I2, R2, and then minus I3, R3, right? And then that's equal to 0, I guess. Okay. And then we could find out we can combine all these resistors together to be R1, 2, 3. So that would be like 10 ohms between them. So, yeah, no, hold up. This is not making any sense at all. I have completely screwed up this problem. Yeah, I don't know what I'm doing at this point. I don't know why I've just blanked. R2 and R3 together, they would have the same voltage. Yeah, go ahead. Who was talking? Sorry. They have, what? Negative 3I4 plus, okay, plus 2I2 is equal to 0. So, okay, so they have, so that's just that loop, okay, plus that, plus, nope, none. Okay. Oh, I see. Oh, okay. I see what they're doing here. That makes a lot of sense. So since R23 and R4 have same voltage, then effectively like V4 should be equal to like V2 and 3, right? And that's where I think they're getting, yeah, V4 minus V2 3 is kind of what they're doing here. Or actually they're kind of doing the opposite in that case, so they're doing V2 3 minus V4. Okay. And that's equal to 0. So that's kind of what they're doing. Okay. So they just did then like I2, and I2 would be the consistent between R2 and R3. So I2 times R2, and then add that to I2 times R3, and then subtract that from, or subtract I4, R4 from it. Okay. And then that is, yeah. And then we got 4 amps here. R4 is 3 ohms. And then these two together, it'd be like 2I2 plus 4I2. So this is 6I2. And then this is equal to 12 basically. And then I2 is just equal to 2 amps. Okay. That's fair. But I'm trying to think, like, you should have been able to pick that loop and you would have been fine, like an overall loop. But maybe it's just because that we don't have the voltage of the battery. I think that might just be the issue. I don't know. Anyway, okay, I'll give that one another thought later, but I just want to make sure that we can kind of get through this. Yeah. Mm-hmm. Yeah. I'm wondering, like, okay, so. Okay. Ooh, I'm wondering if you could have done, like, because we don't know V battery, right? Because we don't know V battery, then we could have said, like, I'm wondering if you could have done this, like, you could have set the two loops equal to each other. You know, like V battery, and then minus, like, I total times R123, and then set that equal to V battery minus I total R14, basically. And then your V batteries would cancel out, right? And this R123, like, I'm just putting that here for now, but this would essentially just be like I total times R1, right? So that would be like 4 ohms, so 4 ohms, and then just, yeah, I guess I'll just add it, not really add, but subtract kind of the I total R2, and that was 2 ohms. Oops. And minus I total 3 ohms, or 4 ohms, my bad. And then the same thing would be kind of on the other side, where it's just I total times 4 ohms, and then minus I total 3 ohms. Would that work? Because then we just have 6, so minus 10 ohms over here, so I total 10 ohms. Yeah, that does absolutely nothing. Okay, screw it. It's whatever. Yeah, I know for a fact that you can solve it like this somehow. It's just I'm not remembering how to for some reason. Yeah, this problem is not fun. I'll take a look at it at the end because I know for a fact you can solve it like this, like the loop stuff. Just pick a loop and then solve it that way, but I'm just not clear on that for now at the moment. Anyway, so I'll just move on to C. C says use the junction rule to determine the current I. Be explicit about your choice of junction. So if we have determined that I2 is 2 amps and I4 is 4 amps, then once again, just kind of by that idea of the current splitting off, right? So if we had, if this will reload here, there we go. So this is 4 amps going up here, 2 amps coming out there, right? So they kind of have to reunite at the end, and then this would be your total current at this output point, which is just 4 plus 2 amps, and that would be 6. So I total 2 amps plus 4 amps, and that's just 6 amps total. But yeah, the junction rule is a lot simpler than the loop rule, because the junction rule is just telling you that like your currents have to kind of add up or reunite once you go through like a branch like that. Yeah, whatever goes in has to come out. But yeah. Anyway, are we good for C so far? Let me move on to D here real quick. So D says use the loop rule to determine the voltage of the battery, right? So for the voltage of the battery, B battery, we now have that battery that we wanted, right? And so we could just effectively just pick up loop now again, right? So, oops. So I know that, pick that one loop, right? So we have I4, R4, that's one loop. And then I1, R1? Yeah. Wasn't that? Yeah, exactly. And that should equal 0. So we're trying to figure out V battery. V battery would then just equal to I4, R4 plus I1, R1. I4, we already determined that to be 4 amps, and R4 was 3 ohms, right? And then I1, we said that was going to be well, I1 would have been 6 amps anyway. Yeah, 6 amps exactly, because that would be the original current that was delivered. And then multiplied by R1, which would just be 4 ohms, right? And then this is just 12 volts plus 24 volts, and that gives you your 36 volts. And that's the voltage of the battery right there, right? So maybe that's what I was screwing up earlier. So if I picked a loop for that part C, or not C, part B for the loop rule, I had like V battery minus I1 R1 minus I4 R4, right, where this was 4 amps like they told us, and R4 is 3 ohms like they told us, right? And you had your I1, that was unknown basically. Yeah, I don't know. I1, R1. Yeah, I mean, I'm basing this off like practice problem example 9 on the reading. You could definitely set loops equal to each other. So, I'm not sure what's going on here. Because you could have set this equal to like V battery minus I1 R1. Okay, hold up. Minus I2 R2 and then minus I2 R3. Okay, there we go. There we go. There we go. That's what I was missing. So let me rewrite that at the end. You could have done this, right? This is the final piece, barring any stupid mistakes. So to figure out these loop problems, right? Gosh, I don't know why I just go stupid mode for no reason. To figure out these loop problems, right? If we refer back to that part B, right, where it says use the loop rule. The loop rule just tells you, once again, right, that once you go through a loop like that, once you pick a loop, you have the voltage drops perfectly between them, right? Between every single resistor that you go through, the voltage that you ended up with should go to 0 at the end of the loop, basically, right? And so, like we were doing earlier, we did like V battery, right? And then we picked that one loop where we said minus I1 R1 minus I4 R4, and that went to 0, right? So the voltage should go to 0 at the end. Now, what I was missing earlier, right, is I think I tried to add up the resistors as if they were in series and stuff, but no. Do not change the identity of any of these resistors, like if they're in parallel, if they're series or whatever, anything like that. So what you want to do is pick a loop first. Let's go through that big loop that just goes through R1 and R4, right? Which was just this, right? This was the big loop, R1 through R4, and that's it. Then we go through the second loop, which is R1, R2, and R3, right? So our first loop, the big loop, was V battery minus I1 R1 minus I4 R4, right? That should equal 0. It should also equal, right, because whichever loop you go through, you should end up at 0 at the end. So the other loop was still V battery minus I1 R1 minus I2 R2, and then minus an extra I2 R3, right? Why do I have I2 the same here? Well, because I2 would be the current that would be going through that branch, right? It should be the same current between R2 and R3 because there's no extra branching off, right? So V battery cancels on both sides, I1 R1 cancels on both sides, and you're left with negative I4 R4 is equal to minus I2 R2 minus I2 R3, right? And this is exactly the setup that they had, where you added up I2 R2 plus I2 R3 minus I4 R4, and that equals 0. That's what I was trying to do earlier. But I think I tried adding up the resistors for some reason. And so at that point, right, this would have been what? Your R2 is 2 ohms, your R3 is 4 ohms, right? So this is 6 ohms times I2, and this is 4 amps times 3 ohms, right? So this is just 12 volts right here. Because 4 amps and 3 ohms, and that's equal to 0. So 12 volts is equal to 6 ohms times I2, and your I2 would be 2 amps. Does that sort of clear it up now? So what I was doing at first was correct. It's just that for some reason I tried adding up the resistors. I don't know why. But does that make more sense about how to approach like the loop rule stuff? You pick 2 loops and you set them equal to each other, where you have V battery minus all of the different resistors voltage drops. Okay, excellent. I'm glad it makes more sense now. I will edit the hell out of this later and just cut out the entire part where I screwed up and then just skip to that part. Yeah. But yeah, let me just reiterate. So you pick two loops. One loop you pick it, and the other loop you pick it. Set them equal to each other, right? So this is our first loop. This is our second loop. First loop went through R1 and R4. Second loop went through R1, R2, and then R3, right? You have to have V battery on both sides because once you do V battery minus the voltage drops across each resistor, it should end up at 0 at the end, right? So this should have 0 on both sides, basically should be the result of either of these equations, right? And then you just effectively just subtract off the voltage drops from each resistor. So we went through R1, so it goes minus I1 R1. You go through R4, it goes minus I4 R4. And then that equals the other loop, which is V battery minus I1 R1 again, minus I2 R2, and then minus I2 R3, right? Why do we keep I2 the same between resistor 2 and resistor 3? Because it's the same current going through them, right? So we define the current based on the resistor that's going through it, right? So current going through resistor 1 would be called I1. Current going through resistor 2 would be called I2. Current going through resistor 4 is called I4. The reason why I2 is kept the same between R2 and R3, right, is because they're along that same branch and they're in series with one another. Now you might be asking, well, if we go from R1 to R4 in that big loop, right, why can't the current be considered the same between them? That's the mistake I was making earlier, right? It's because R1 and R4 are not in series with one another. You have to maintain the identity of each resistor, how they are in series or in parallel with one another, right, based on the original circuit. R1 and R4 are not in parallel with one another. They're not series with one another, right? It's an unidentified relationship, kind of, until you simplify the circuit down. That's the idea. So all loop problems, the loops must be set equal to each other. And yes, you isolate the currents and solve for whatever you want to solve for. And in this case, you can see really easily that I1 and R1 on both sides will cancel out. V battery will cancel out. And then you're just left with the different voltage drops across the different resistors. And then you can just solve for whatever current you want to solving for. Does that make sense? Okay, awesome. All right, well, that's good for resistors, I guess. Someone wanted to go over sheet charges, right? Okay. Do you have a specific problem in mind? Mm-hmm. Okay. So is it just like the electric field kind of that you're having trouble with? The idea of electric field of a sheet charge? Okay. Give me 1 second. I want to pull up the reading as well. So like maybe I can pull up like an example problem or something like that. Oh, quiz 8. Okay. Let me take a look at quiz 8. Or is that okay, so some electric field problems. Okay. So let me look at quiz 8 then. Okay, I have one of the professor's quizzes pulled up. It might be different, slightly different between professors, but quiz 8, electric field problems and stuff. Okay, so I see sheet charges for that first problem, right? So generally, for a sheet charge, right, I want to pull up the equation sheet here too so I can reference that for you guys. So if you look at your equation sheet, right, there are different electric field equations based on the context that we're looking at, right? So under the electric field heading, you have electric field at a point, at a specific point. You might have electric field for a line charge, You might have an electric field for a sheet charge, or you might have an electric field for a ring charge, right? So for electric field of a sheet charge, E sheet, right, it's equal to the absolute value of the charge divided by 2 times the area of the sheet times the permittivity constant, right? Now, Q over A, we define that to be the sheet charge density, right? And we define that as sigma. And we take the absolute value of sigma whenever we have that given to us. And that's divided by 2 times the permittivity constant. Now, you notice that this equation doesn't have any relationship with distance at all, right? There's no radius, there's no r here in the equation. So whatever point you're looking at, the electric field should have a constant magnitude at every single point, right? So it doesn't matter what, radius or what, distance we are away from the sheet charge. It's always going to be a constant magnitude for the sheet electric field, right? So if we were to take a look at quiz 8, look at problem 1, part A, right? 1A. Then we realize that it says positively charged sheet has a surface charge density of sigma 1 is equal to positive 2 microcoulombs per meter squared. What are the magnitude and direction of the electric field at a point P located 4 centimeters above the sheet? What should be extraneous info here? What does not matter at all? They told us that sigma is equal to 2 microcoulombs per meter squared, and they said the distance away is 4 centimeters above the sheet. What doesn't matter here? The distance, we don't care about it, right? So if they're just asking us for the direction and the magnitude of the electric field at that point, then it's a very simple sigma over 2 times the permittivity constant, right? And it's the absolute value. So this was negative 2 microcoulombs per meter squared. You convert it to just positive 2, right? And we want things to be in SI units, so this is 2 times 10 to the negative 6, right? And then you divide by 2 times your permittivity constant, and boom. And this should be directly upwards, right? So anywhere, like for a sheet charge, wherever you have the point located, it's usually just going to be directly upwards like that from the sheet, perpendicular to the sheet itself. Part B, for example, they're saying another charged sheet is placed 8 centimeters above the first sheet with a charge density of negative 5 microcoulombs per meter squared. What is the magnitude and direction of the electric field at point P halfway between the two sheets, right? Once again, doesn't matter for the distance. Does the distance matter here? No, right? So we have effectively uniform electric field generated between these two plates here, right? E1 and E2. Now, if we want to figure out E net, right? E1 plus E2, right? Now, what do I want to say here? So, since we are concerned with just the absolute value of the sheet charge density, both of these values should technically be positive for the electric field. You adjust whether it's negative or positive in your equation for E net based on the direction the electric field is pointing for each sheet. So if I have a negative sheet like this, negative, 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 and then we have positive, 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 right? The convention for any charge here, right? For any, like if you have any sheet charge, line charge, even if you just have a point charge, you draw the electric field lines in a way that would be directed how a positive test charge would react to that charge, right? So if I have a little positive test charge like this next to positive charges, how do you think that positive test charge is going to move with respect to the positive charges in that sheet charge? Yeah, so it should just be moving up, and without even going into that, it should just be repelled, right? So the positive charge should be repelled by that positive sheet charge, right? The test charge should be repelled by the sheet charge. It should move upwards, away from it, right? How about for the negative charge? For this negative sheet charge here, how would the positive test charge react? Exactly, would be attracted, so it would also move upwards, right? So the idea is for electric fields, your electric field lines point in a direction as to how a positive test charge, if it were there next to the electric field, how that positive test charge would react, right? So if I have a positive test charge here, then the positive test charge would react by moving away from the sheet charge in that sense. So the way they define it in the textbook is that they say that electric field lines for positive charges point outwards and away from the charge. So point outwards and away from the sheet charge here. And then for negative charges, it would point inwards, right? Because if I had a positive charge here, it would want to move inwards towards that charge. If I had a positive test charge here, it would want to move inwards towards that negative charge there, right? Same thing if I placed a positive charge at the bottom there, right? If I have a positive charge here, it's going to want to get repelled upwards. If I have a positive charge there, it's going to want to get it repelled downwards, right? So that's the idea. The electric field lines point in a direction by convention as to how a positive test charge would respond to the charges in that sheet, or even if you had like a point charge, right? If I just had a source charge like this is my source charge, and this is my test charge. This is capital Q, this is lowercase q, right? I draw the electric field lines in a way to show how the test charge would react. So test charge, positive next to positive, it would want to move away from it, right? So it would go this way. So the electric field lines point outwards from the source charge. Now, if it were a negative charge, right? If this were a negative charge that we're dealing with, and this is positive, it would want to be attracted to it. So the electric field lines point inwards for a negative charge. That's the idea. So, with that being said, right, you can see here if I had a point that I was looking at here, and once again, that point is usually just defined as a positive test charge by convention, then that positive charge would move upwards from the positive sheet charge, and it would also be attracted upwards by the negative sheet charge. So your E net, right, is made up of an E1 pointing upwards and an E2 pointing upwards, right? So E net here, like I said, whether you have E1 as positive or E2 as positive or negative, right, is just dependent on the direction. If it's the positive y-axis or if it's the negative y-axis or if it's the positive x-axis or the negative x-axis, right? So if it's moving upwards, it's positive for your E. If it's moving downwards, it's negative for your E. If it's moving to the right, it's positive for your E. If it's moving to the left, it's negative for your E, right? So in this case, both of them are positive, right? Because we're just taking the absolute value of each one, and then the sign in between, like I said, is just going to be the direction. So since they're both up and up, right, then you just add them up, right? So E1 plus E2, and then you're done. Now, let's say if I had a charge like down here, what would be the directions of the electric fields felt by that positive charge? Or if I just said, without even saying a charge, if I said point P was down here, what would be the directions of the electric fields? And then keeping in mind this is 1 and this is 2. One is down and 2 is up. Excellent. So 1 is going to be moving downwards like this. That's E1 because that the point charge here, or the test charge, I mean, at point P, once again, by convention, it's positive, right? A positive charge would be repelled downwards because of this sheet charge. And then that same positive charge would have been attracted upwards because of that negative sheet charge, right? So if we wanted to write an E net for this, we'd say E net is equal to absolute value of E1, but it's negative on the outside because it's downwards, and then plus absolute value of E2, and that's positive here. That plus is positive here because E2's electric field would be pointing upwards because the charge would have been attracted to that negative sheet. Does that make sense so far? Okay. Does that make sense as well, Eric? And then it's saying what is the magnitude and direction of the force on a charge of Q equals 3 nanocoulombs at point P. So if we did that, right, and we know that force, there's an equation for force relating to electric field, and that's Q, which is little q, that's your test charge, multiplied by our electric field. So we know our electric field, and we can just multiply it by that 3 nanocoulomb charge. And instead of 3 nanocoulombs, we want to say 3 times 10 to the negative 9 coulombs. So we want everything to be in SI units, right? And then you just figure out the force that way. Now, with that being said, right, you want to also account for the direction of your force, right? You want to account for the direction of your force. Now, once again, with the electrostatic force, similar to the electric field, the electrostatic force is going to be pointing in the direction of how the positive test charge would react relative to the electric field or relative to the forces acting on it, right? So in this case, the positive test charge at that point P would be effectively feeling a force or an electric field, right, upwards from E1 and upwards from E2, right? So it's getting repelled from that positive sheet below and it's getting attracted to the negative sheet above, right? So the force, the net force would technically just be upwards at that point, right? So that's the idea. Now, for, what do I want to say? So if you look at the equation for the electrostatic force that factors in the electric field, you'll notice that there's no absolute value sign around E. There's no absolute value sign around E. So, like I said, if I had an example where I had the point P down here, I would have to find out what E net actually is and then plug it into my equation. Because maybe if that positive sheet is really, really strong, it could be repelling that test charge more than the negative sheet is attracting that test charge. So you might have like -4 for that electric field and then only +2 for that second electric field from that negative sheet charge. And so your net would be -2, which would mean downwards, right? So that's the idea there. You have to figure out your E net to be able to figure out the direction of your net force or your electrostatic force, right? Because, like I said, if you have a very, very strong electric field due to that positive sheet, it could overwhelm the electric field due to the negative sheet, and the test charge, the positive test charge, could move downwards. But yeah. Can I check my iMessages when I get a chance? One sec. Yep, I can share the Google Drive here. I'll post it actually to the, what's it called? To the chat here. Give me 1 second. So 132 resources. And then let me just copy the link. And I'll paste it here. There we go. Okay. Now, does that make sense with regards to the electrostatic force stuff? Like, your net force, like direction, would have to be based on the direction of the electric field? Okay. All right. Now, what was that last part? It was part D, right? And so part D is what it says: at which of the following points is the electric field 0, right? So if we're looking at when the electric field is 0, then once again we kind of have to factor in the directions of the electric fields at every single point, right? So once again we have to think about these points as being positive test charges because that's the convention, right? So if we have a negative sheet charge like this and a positive sheet charge like that, and we look at point C and point B, right? And what else here? So looking at point A, what would be the direction of the electric field for 1 and 2? How would 1 point and how would 2 point? How would the electric field for... Yeah, go ahead. I said, how would the electric field lines point at point A for sheet charge 1 and sheet charge 2? Exactly. So 1 is down and up for 2. Excellent. How about for C? Right, so 1 and 2 are both upwards. Excellent. How about B? Up for 1 and down for 2. Excellent. So it says, at which of the following points is the electric field 0? Well, by process of elimination, C should not be 0. Why? Because both of them are pointing upwards, so you would have a net electric field at that point, right? They would add up together. But 1 and 2, points A and B are a little bit iffy because one's pointing upwards, one's pointing downwards. We're a little bit unsure here, right? Now, what do you notice about E2? What do we know about E2 and E1? One is larger than the other, right? They're not perfectly canceling out. One is larger, one is smaller. Which one is larger? Is E2 larger than E1? Remember, we're thinking about things in terms of absolute value. No, it wouldn't be, because we're factoring in absolute value, remember? So the negative plate would actually be stronger because it has an absolute value, at least, or a magnitude of 5 microcoulombs per meter squared as its charge density, right? So E2 is larger than E1 because if we were to calculate this out, sigma over 2, or not equal to, but yeah, and sigma over 2, right? Remember, the equation calls for the absolute value. Oh, I guess, okay, so I see. It might be because you guys have a different quiz. So, well, on your quiz then, Eric, which, because I'm looking at Spilo's quiz, so on Espinosa's quiz, which one is larger than the other? Or, like, what are the values? Because I want to make sure. Okay. And that's -3, right? -3 microcoulombs. Okay, yep. So in that case, yes, E1 would be greater than E2 at that point. Yep, exactly. Right? So this might be a little hard because the quiz sheets are a little bit different, but the idea is that I believe none of the above would be correct. So none of them should have electric field of 0 because clearly one overwhelms the other. Right? Does that make sense? So you're going to have a net because one overwhelms the other. Otherwise, like if they were the exact same magnitude, then because one points upwards and one points downwards, then you have them cancel out, and then your electric field might be 0 at A and B. Does that make sense? Okay. Does that clear things up a little bit more about how to approach sheet charges? Okay. Mm-hmm. So they would have to have the same magnitude, but it wouldn't be through the center, right? Because remember the center, you would have, you would actually have a net electric field because the direction would be both pointing either upwards or downwards, right? So if I had this positive plate on the bottom, negative plate on top, then if this is a positive test charge, right, be pointing upwards for E2 and pointing upwards for E1, right? And even if I had a positive plate on top, for example, and a negative plate on the bottom, then at point P here, it would be downwards because of 1 and downwards because of 2. Does that make sense? Exactly. So you want to have one going upwards, one going downwards, and that pretty much only happens like anywhere not between the two plates. Right? So this is like inside and this is outside, basically, right? And so you would only find the electric field 0 outside of the plates, and if those magnitudes of the electric fields are the exact same. Because in that case, then one would be pointing upwards, one would be pointing downwards, and they would cancel each other out because they have the same magnitude, right? So remember, these equations, like when you're solving all this stuff, make sure to look at your equation sheet to figure out if you need to be plugging in absolute value or not. And in this case, when you're doing these net electric fields, you are doing absolute value only, and your directions, like whether you have a negative or a positive sign, is just dependent on whether the electric field is pointing upwards, downwards, left, or right. Because you could also have these plates vertically, right? You could have positive, positive, positive like that, negative, negative, negative like that, right? So in that case, if you have a positive test charge like this, then it would be going this way. This is 1 and this is 2. So 1 and 2 would go that way, right? If you had a point here, then it would be 1 would go this way and 2 would go that way, right? So going to the right would mean a positive electric field, and then going to the left would mean a negative electric field, right? Because positive x-axis, negative x-axis, right? So that's two ways of doing it as well, because you could either have vertical plates or horizontal plates. But the idea is that if you ever want to have a net electric field of 0 with these two plates like this, whether horizontal or vertical, the point has to be outside of the electric plates or the electric field plates or the sheet charges, right? So this is like the inside or like between the two plates. So it has to be outside, and the magnitudes have to cancel each other out. Does that make sense? Okay, awesome. Oh, my neck. Alrighty. What? Bro, what? Okay, I guess. Okay, all right. Um, anyway, yeah, so hopefully that clears up the sheet charge stuff. Um, so after the sheet charge stuff, I don't think we had anything else that people wanted to go over, at least specifically for now. But let me scroll up and see if there was anything else. It seems like the consensus was that the circuit stuff was the most bogus stuff. So hopefully, like, I've done a couple problems now that it's starting to make a little bit more sense. Ranking problem. What ranking problem? Oh, 3A. Yeah. I remember that now. Okay. On the practice exam. Which practice exam? Oh, wait. Hold up. So let me see here. Let me go to 132 and then to... Oh, the one me here did. Okay. Did he not explain that one? I'm just curious. Like, I'm wondering. Oh, we got some conflicting. Oh, he went over the long problems, I see. Ah, damn. All right. Yeah, I thought he went over the entire practice exam. I would have, like, done this extra stuff, I guess. Okay. Damn, then I'm a real G then for sitting through and doing the entire practice exam. Like, I don't mean to hype myself up. All right, so let's look at problem 3A. Ah, okay, fair. So yeah, he did go over basic concepts, so that's good. Okay. Yeah, I have no room to talk. I was absent for this unit, so. All right, so problem 3, pulled it up now. Problem 3A. This is practice exam, just a regular practice exam. No, all the peer leaders that have been here before me are the GOAT. Amit is the GOAT. Mihir is the GOAT. Everyone else is the GOAT. I'm just chilling. I haven't built any sort of reputation or legacy compared to them. They've been doing it way longer than I have. Anyway. So 3 capacitors of capacitances C1, C2, and C3 are connected in 4 configurations as shown. In some configurations, an insulator of dielectric constant K2 has been added to the capacitors. Rank them according to their equivalent capacitance from largest to smallest. Right? Okay. So, this is a very interesting conceptual problem here. This is really fun. So, one of the most important things you have to understand for figuring out capacitance is the fact that if you place a dielectric between 2 capacitor plates, you are increasing the capacitance of that capacitor, right? So there's an equation, and I don't believe it's on the equation sheet, but basically, like C with a dielectric, right? Your capacitance with a dielectric is equal to your capacitance without a dielectric, right? Multiplied by your, what's it called? Your dielectric constant, right? Your kappa. So, what did I want to say? So, if we're looking at each and every single one of these capacitors here, right? Then between A and B, right? Between A and B, which do you think is going to have the greater capacitance for every single capacitor? Like let's forget about equivalent capacitance for now. Let's just look at each capacitor alone. Which one is going to have the higher capacitance? With the dielectric, right? So B should have higher capacitance for every single capacitor relative to A, right? How about C and D? No, I mean, like this is your original. Like this is without the dielectric, so this would be original, and you multiply it by dielectric constant. No, you're good. No worries. Let's see here. What do I want to say? Give me 1 second here. I just got to do something real quick. 1 minute here. I just have to share something with another student for their Google Drive. Okay, done. So, yeah, going back to C and D, right? Which one has the higher capacitance per capacitor? C or D? D, right? So D and B are going to have higher capacitance per capacitor, right? But now we got to look at equivalent capacitance, right? So for capacitors in series, how can we figure out the equivalent capacitance, right? How can we combine capacitors in series? How can we do that? Excellent, right? So whatever you do for a resistor, you do the exact opposite for a capacitor. So if we added up resistors in series just normally, then we'd have to add up the reciprocals for capacitors in series, right? So 1 over C1 plus 1 over C2 plus 1 over C3, etc., right? Well, you can try and plug in like sample values to figure this out, and I think that'd probably be the best way. So if you were to say, for example, like, I don't know, let's say all these capacitors are the same value, right? They're all like 2 farads or something. So 1 over 2 plus 1 over 2 plus 1 over 2, right? Let's say that's the capacitance. Let's say 2 farads is the capacitance of each capacitor without a dielectric, right? So this would give you what? 1.5, right? Actually, I want to do something that's a little bit easier to work with. So maybe let me instead of taking all 3 capacitors together, I'll just do 2 of them, right? 1 over 4 plus 1 over 4. Let's say the never mind, actually, my bad. 1 over 2 plus 1 over 2 is without a dielectric. Without dielectric, right? Without a dielectric. You add them up, that gives you 1. Reciprocal of 1 is just 1. Boom, done, right? Well, what if I inserted that dielectric and now my capacitance has doubled, for example, right? So now I have a capacitance of 4 farads per capacitor. So this is 2/4, right? And that's just 2 then. Well, it's 1/2, but the reciprocal of that is just 2, right? For your overall capacitance in series, right? So you realize then, by plugging these values in, that you know that B would be greater than A, right? B is greater than A. So that's one part here. Now, are B and A greater than or less than C and D? B and A are less than, exactly, right? Because adding up the reciprocals of the capacitances will get you a lower number than if you just added up the capacitances normally. And that's what you do for a parallel set of capacitors, right? For parallel resistors, you add up the reciprocal, but you do the opposite for capacitors. For parallel capacitors, you add them up normally, right? So instead of doing 1/2 plus 1/2, we would do 2 plus 2, right? And that's 4 instead of 1, right? So that means C and D are greater than B and A, right? Well, how about which one is greater, C or D? Well, D would be greater than C. Excellent. Why is that? Because of the dielectric, right? So if we place that dielectric in, right, if we had each capacitor have a value of 2 farads, it would be 2 plus 2 plus 2, so that's 6, right? Well, what if each one had a dielectric in between, so it doubles it, so now it's 4 plus 4 plus 4, right? So now it's 12. Well, 12 is clearly greater than 6, right? So this is 12, this is 6. What is B? We said that was 2, and this was 1, right? So if you wanted to plug numbers in, you could easily see then that ranking. And I think that's probably the best way to go about it. But from a more conceptual standpoint, you can immediately identify that C and D are greater than A and B because adding up capacitors in series is always going to give you a greater amount than you've added them up in. Wait, hold up. Did I say that the other way around? Adding up capacitors in parallel will always give you a greater value for your capacitance, your equivalent capacitance, than it would for man, my throat is dead. Finding out the capacitance, the equivalent capacitance for a set of capacitors in parallel will always give you a value greater than if you were to find the equivalent capacitance in series, right? So adding capacitors up in parallel, you just add them up normally, like C1 plus C2 plus C3, right? But if you add them up in series, like you do in A and B, then you add up the reciprocals. So it's 1 over 2 plus 1 over 2 plus 1 over 2 instead of 2 plus 2 plus 2, right? So you can immediately identify that C and D have to be greater than A and B, right? So you could write like for 1, 2, and 3, and 4, you could have said C, D, A, B, right? And then the top half is correct, the bottom half is correct, but now you have to adjust the ranking between each set, right? So within capacitors or between capacitors that are parallel with each other, right, I have C and D. D, when I place an insulator, when I place a dielectric, it's supposed to increase capacitance, right? Well, in that case, it just means that D is greater than C, right? Because if I'm adding up the capacitors normally, right? If I'm adding up the capacitors normally, 2 plus 2 plus 2, well, if I double the capacitance by using an insulator, then I do 4 plus 4 plus 4, right? So that's much greater. So D is greater than C. Then I can plug in units at that point, or plug in values at that point to make things easier. If I'm comparing A and B, right, then placing an insulator inside only makes the denominator bigger. Making the denominator bigger, what'll that do? That ends up still increasing your equivalent capacitance, right? So B would be greater than A. So break it off at first by looking at it conceptually, knowing that parallel capacitors are going to give you much greater equivalent capacitance than series. And then within every set of two, look at how to rank them based on, you can just plug in values and compare the capacitances. Does that make sense, Thomas? Okay. Oh, man. Alrighty. Did you want to do 3B as well? Or, that one's not too bad. All good on your end? Okay. I can just do it verbally, like C4, 5, and 6. You should see that those are in series, right? And if they're in series, they're consecutive, they're continuous. And so for capacitors in series, you just add them up using the addition of the reciprocals, right? So 1 over 3 plus 1 over 8 plus 1 over 2. And then that would give you the equivalent capacitor. Well, first, then you'd have to take the reciprocal of that, right? So 1 over 3 plus 1 over 8 plus 1 over 2. Whatever you get there, you take the reciprocal of that, and that's C4, 5, 6. All right? So that's how you find the equivalent capacitance for that one. Any other questions about this practice exam for the short problems or anything else? Alexa, I saw you typing earlier, so I don't know if you had a question or... Okay, you're good. You sure? Yeah, so I said earlier about the written homework. The written homework, I felt like, I don't know. The written homework that I had was okay, but the written homework that you guys have, I feel like is a little bit more like just drawn out and complex and stuff. And I feel like quizzes in the online homework for this chapter at least are a little bit more representative. Yeah, I had an entirely different like written homework. Some parts were similar, but like yeah, just different written homework. Um, but yeah. Um, but yeah, any questions about this practice exam at all? Seems like it's a no. So, and I don't see any other suggestions for any other topics at the moment. Unless someone wants to speak up in the next like minute or two, because I want to look at. I'm gonna pull something up here in my end to see if there's some things I want to go over. I think we covered current and resistors pretty well, and as well as capacitors. So that covers chapters 10 and 11. So let's see here. 10 and 11 I think is covered pretty well so far. Unless someone wants me to do any extra practice for that. How to find electric fields for point in practice problem chapter 9. Okay, let me pull that up then. Chapter 9. Content review. All right. Chapter 9 is electric potential and electrical energy. You want to find electric fields. Okay, hold up. I think that's more like energy and stuff like that, and voltage, not as much as I think you might have meant chapter 8. Is that the one? Because the chapter 8 is electric fields. So electric fields, that's on chapter 8, right? And for electric fields in this chapter, there are a couple different like electric fields you can calculate. You can calculate electric fields for a point charge. You can calculate electric fields for a sheet charge. We kind of covered sheet charges already. Line charges aren't as common, I think. Those usually don't pop up. Ring charges definitely don't pop up. I don't want to like say that and just jinx it, but it's very rare for a ring charge to pop up. If it does, like I assume it would just be a very simple kind of like, here are the values like the radius and stuff, and you just plug that in. It's fine, because there's like virtually almost no practice with the ring charge stuff. There's one problem on the reading that covers it, but otherwise, yeah, I mean, sheet charges or surface charges, we kind of covered that already. Line charges, we haven't, and then there's point charges. So yeah, two most common ones probably going to be point charges and sheet charges or surface charges, right? Now, for a point charge, when you're figuring out the electric field at a specific point, once again, realize that the convention is that this point is a positive test charge. So we imagine that there's a positive test charge there. In reality, every single charge would probably create its own electric field, right? But when we have a specific point, they want us to assume or pretend, basically, or imagine that there's a positive test charge there. When they're asking us to figure out the electric field at that specific point, we are calculating the net electric field acting on that point, right? Or basically, in other words, the electric field that this point or this imaginary test charge would feel at that point, right? We are not considering what electric field is being generated at that point, right? So if I had a point A, B, C here, right, where B is a positive charge, A is a negative charge. Let's say this is 6 nanocoulombs, this is 5 nanocoulombs, and they're asking you to find the electric field at point C. Well, at point C, theoretically, there could have been a charge that's like 7 nanocoulombs, right? Maybe, yeah, let's say positive 7 nanocoulombs, right? So at that point, that charge would be creating its own electric field. However, we do not care about the electric field that it's generating at that point. We care about what it's feeling at that point, right? Don't care about generating at that point. We only care about what it feels, right? So we only care about what it feels because at that point right here, it's feeling an electric field from B, right? An electric field from A, right? So when they say at a specific point, they want you to imagine that there's a positive imaginary test charge there, right? And then draw your electric fields accordingly. How do you draw them accordingly? Well, you draw the electric field lines in a way to show how that imaginary positive test charge would have reacted to the other two charges, right? So if I have point B and point C right here, if I said that this is a point and I'm imagining by the convention that this point is a positive test charge, how would C react to B? Would it move upwards, downwards, left, right, at an angle? What would happen? Move to the right, right? So it gets repelled by B, right? How about A? How would the charge react to A? Excellent. So move at an angle. And exactly what angle? I want to say like, I don't want to say like 30 degrees or 50 degrees or whatever, but like roughly, like how would it go? Okay, southwest. Awesome. Cool. Southwest, right? And it's pointing directly along the axis between that point C and point A, right? So that has like a y component and x component, right? But we want the direct shortest distance between them, right? Which is this axis here. Informally, like I like to call it like the electric field axis, which is just the shortest 2 points between the two charges or the 2 points, right? So we have an electric field going this way and an electric field going that way, right? So here's a positive like EX from B, a negative EX from A, and a negative EY from A. And there's no EY from B, right? That's just 0 because you're only moving on the x-axis as a result of B, right? So really you're just drawing your electric field lines in a way to show how, if there was a positive test charge at that point, how would it react, right? It would get repelled by B and it would be attracted by A, right? That's the idea here. So it's kind of basically similar to how you would draw your electric force lines, right? So if I told you draw me the force of QB on QC, right? You would draw it the exact same direction. QB on QC. If I told you to draw me QA on QC, you draw it in the same direction, right? It's what and once again, like force of like QA on QC just means, right? What does QC feel from QA? How does QC react to QA, right? So that's the notation you're always going to see. You're going to see like a charge on another charge, right? Blank on blank. When you see that type of notation, you kind of flip it the other way around, right? So instead of force on QA on QC, what it means, like, you're not really flipping anything around. It's just a better way to understand it. It's just that notation just means that I want to figure out or draw my force in a way that shows how does C react to A. So the notation goes A on C. I want to figure out how C reacts to A. So on, and this is reacts, right? And this is what you're actually looking for. This is what you actually draw, the reaction, right? So C reacts to B by moving to the right because it's repelled by B. It does not want to be near it. C goes down and to the left, right, southwest, along that electric field axis because it wants to be attracted to A, right? That would be the force of A on C. And that would also be the force of B on C as well, like I mentioned earlier, right? So for either electrostatic forces or electric fields, you want to draw your directions in a way as to how the charge would react at that point. Now, once again, if it just says point A, draw me the electric field line at point A, or draw me the force at point A, right? Then you're assuming that point is just an imaginary positive test charge. So you draw it in a way as how a positive test charge, if it were there at that point, how it would react. Otherwise, if you threw in a negative charge, right? If you threw in a negative charge, like if you had A, B, C, right? And this was negative, and this was positive, this was, let's say this is negative as well, right? Then negative would be attracted this way, and your negative would be repelled that way, right? So that's if they specified that the electric field, or that the point here, the point C, is a negative charge. So you just draw the electric field line based on how that charge would react to the other charges around it, right? Now, if you think about it, right, then what's it called? Your charge at point C, if they told us this was a 7 nanocoulomb, negative 7 nanocoulomb charge, and this was positive 6 nanocoulombs, and this was negative 5 nanocoulombs, right? If they said, what's the electric field line, or what's the electric field strength at C, or what's the net electric field at C, then I would only factor in EA and EB. I do not calculate EC in my net electric field equation. Why don't I do that? Because once again, I'm only concerned with what point C feels, not what it generates. Right? So if I'm doing E net, I would only do EA, right? And then EB. Right? And it's not exactly a one-to-one conversion like that, because the issue is that we have X and Y components of each one, right? So if this was a negative charge, it would move to the left, attracted this way, and this is a negative charge here as well, so it would be repelled that way, right? So we'd have a negative EAX, and there's no EAY is equal to 0 because you're not moving along the y-axis. And we also have a positive EBX and a positive EBY, right? So effectively you would have to do like E net X is equal to EAX, right, minus EBX, right? Or I think I got that the other way around, but you get the idea. Let me actually adjust that. So BX minus EAX, and then E net Y, well, since there's no EAY, it would just simply be equal to EBY, right? And then you can just use like Pythagorean theorem to figure that E net out, because you know that E net X squared plus E net Y squared is equal to E net squared. And if you just take the square root of that on both sides, you should get that that's equal to E net, right? So that's the idea there for electric fields of points, right? You draw the electric field lines at that point based on the convention that it's a positive imaginary test charge there. Draw the lines as to how the positive charge would react to the charges around it. But yeah, and then another important thing to realize is that when you're calculating the electric field of a point charge, you're using this equation, K capital Q over R squared, right? Capital Q, this is a source charge. So this would be every single charge not including C, right? There's every single charge not including C. Little q is that imaginary test charge that we're talking about. So once again, this shows you that the electric field at that point is only dependent on the other charges generating the field, not the charge at that point that would be generating it, right? So once again, this R here as well, this R is the direct distance between each point, right? So if I have, let me clean it up here. So if I have A, B, C, right? Then the R that I'm looking at is this direct R, and the R I'm looking at here is this direct R, right? I can't say, like, if I was given 3 and 4 centimeters, right, here, I can't say R is 3 centimeters. I can't say R is 4 centimeters. I'd have to do Pythagorean theorem to figure out this direct distance in between, which would be 5 centimeters, for example, right? That's my R. What else did I want to say here? And then the final thing is that your Q, your capital Q here, is going to be only the magnitude, only the absolute value of the charges, right? So even if I have positive 6 nanocoulombs here and negative 5 nanocoulombs there, I'm only plugging in positive values. The negative values kick back in when and only when you are trying to figure out that E net, right? E net X and E net Y. And you add a negative sign, for example, right? Or you have a positive sign only dependent on the direction that the field is pointing in. So if I had this, let's say, let's say for 6 nanocoulombs, right? If I had, what do I want to say? My electric field, let's say that's newtons, it's newtons per coulomb, isn't it? Yeah, newtons per coulomb. So if I had 6 newtons per coulomb, right? And that's my EAX, right? And if I were to figure out the X component of my electric field due to B, let's say that was 5 nanocoulombs, or not nanocoulombs, 5 newtons per coulomb, right? Well, one is pointing to the left and one is pointing to the right. I figured out the absolute value of each one, right? I've done my KQ over R squared. My Q's were both positive, and I figured out that this is 6 and this is 5, right? Then when I'm doing my E net X, I can add back in the negative signs, and it's only based on whether it's pointing on the negative x-axis or the positive x-axis or the positive y-axis or the negative y-axis, right? So if it's positive x-axis, right, it would be a positive electric field. If it's negative x-axis, then it's a negative electric field, right? So this would be like negative 6 plus 5, right? This would be like EAX. This would be negative EAX plus EBX, right? Or you can do the other way around, like EBX minus EAX, right? Because this is negative x-axis. This is positive x-axis, right? So that's how you would do that. You only assign the signs at the end when you're trying to figure out, okay, is this negative x-axis, positive y-axis, negative y-axis, then you throw in your signs. Otherwise, look at the equation sheet again, and if you're not sure, double check the equation, right? From that equation, we see we're taking the absolute value of the charge. So we don't care about the sign until the very end when we're trying to figure out directions. Does that make sense? I see a couple questions here in the chat, so I just want to make sure that that makes sense so far, and then I can answer that. Number 2 on quiz 7. Let me pull that up, and maybe you can try and do that as well. Yeah, how to find X and Y components of an electric field. Yep, I can do that. Oh, man. My throat is on fire. And Shireen, for the difference between... Okay, you got it. That makes sense now with the electric field and vectors and stuff. Yeah, I'm reading that comment here. So, yeah, you basically, for electrostatic force or electric field, you're going to be drawing the direction of the force or the electric field based on how the charge would react to the other charges around it, right? Whether it would be repelled or attracted or something like that. But the equations will be different, right? So the equation for electrostatic force is KQ1 Q2 over R squared. So we have to factor in both charges that are interacting with one another. and you're using the absolute value of both of those charges, by the way. But for the electric field, you are using kq over r squared, where you're just factoring in the electric field that charge is feeling from other charges around it, right? So if I had a charge q1 and then q2, and I want to figure out what is the electric field that at q2, for example, right, or at point B or at point A or whatever, then I would take k q1 over r squared, and that's my only electric field that I'm feeling, because that's what I'm feeling. I'm not worried about what q2 is generating. No, I don't think you'll have to find like a problem where you have to work backwards from the angle and have to find x and y. I doubt that. I mean, you could possibly, but it's like that'd just be weird, I think. But yeah. Oh, TA asked if you know how to do that. Well, okay. Let's see here. Does it make sense so far though, like this stuff? Like the how to draw like electrostatic force and electric field lines. Does that make sense for everyone else as well? I just want to make sure. Let me see some thumbs up or yeses in the chat or whatever. Okay, awesome. Well, that's one, I guess. But all right. What else? Okay, so someone was asking like working backwards from the angle, having to find x and y. All right, so let me try and think here. So we're saying if you had an angle, and then what, like if you had the electric field already determined? Or what exactly? Like to what extent are we looking at here? Okay, I think we should just ignore this. Okay, fair enough. Well, from a like just general kind of standpoint, I guess if you were only given the angle 45 degrees, right? And you wanted the x and y components, then let's say if they told you that the force like you had q1, q2, and they said the force between them was like 2 times 10 to the 3 newtons or something, right? Then you could do 2 times 10 to the 3 newtons times sine 45, and that would give you the y component. So that would be like Fy, and this would be Fx, so it would be 2 times 10 to the 3 newtons times cosine 45. Is that kind of what you were asking, or is that a little bit different? Is that it? That's honestly how you would, that's what I'm thinking of what the TA meant by that, is if you were given the force and you wanted to find the components, then you just multiply by the trig identity. Yeah, no, I'm looking at the quiz 7 right now. That's the one I'm kind of referencing. Yeah, so you just take your force and multiply by sine 45 to get the y component, right? Or essentially just opposite to the angle, whatever that is. And then times cosine 45 to get the x component to do that. What else here could they be talking about? And if you had Fy and you had Fx, then that's absolutely right. If you take the inverse tangent of Fy over Fx, that would give you the angle. Right? So if I took inverse tangent of Fy over Fx, I would get the angle 45 degrees or whatever. Does that make sense? That's just from like a general mathematics and geometry standpoint. All right. Yeah, I can take a look at quiz 7 now. So quiz 7 is the multiple charges. So, and it's problem 2, I think. Yep. So Q1 and Q3, they said Q1 is positive, Q3 is negative. So this is Q1 is positive, Q3 is negative, right? And the distance between them, this is like the direct axis, it's 2 centimeters. And the angle between them is 45 degrees, right? They want you to figure out, this is Q1 and this is Q3. They want you to figure out the force of Q1 on Q3. Or not, that's not what we want to figure out, my bad. It says the force of Q1 on Q3 is 1.42 times 10 to the negative 5 newtons. And now it says determine the x and y components of the force. Okay, so that's probably what you were talking about, Shireen. So, yeah. So, yeah, this is pretty much what I was talking about earlier, right? So, you were given the force. They said force Q1 on Q3. And that's equal to 1.42 times 10 to the negative 5 newtons. What does Q1 on Q3 mean? How can we, like, translate that to something that makes sense to us? What did I say we could translate to earlier? Not quite. How Q3 reacts to Q1. So what is Q3 feeling from Q1? Exactly. You got it flipped around. Yeah, no, I'm just saying like the, yeah, it is attraction. Yes, that's right. I'm just saying like how would we like word it? Like we have to say instead of Q1 on Q3, we can say how does Q3 react to Q1? Because that'll help you like draw the directions. And so Q3 would react to Q1 by moving towards it this way, along that axis right there, right? And then we want to figure out the x and y components of the force. So this is just taking 1.42 times 10 to the negative 5 newtons and times sine 45 to get my Fy, and then times cosine 45 to get my Fx. Does that make sense? Okay. And then B, it says calculate the angle phi between the x-axis and the line connecting Q2 and Q3. We want to find the angle between Q2 and Q3 like that, right? So let's see here. Yeah, so for this one, we have Q3 is what? Q3 is negative. Q2 is positive, so here's Q2, Q3. There's the axis between them, and then this forms with, this has like a x-axis here, right? And then they're looking for this angle, phi. And they know that this is 3 centimeters and this is 1 centimeter, right? And this is the same here, 3 centimeters and this is 1 centimeter. How could we figure out this angle? Any ideas? Inverse tangent, right? So we can take inverse tangent, which is opposite over adjacent, right? So if we're looking at this angle right here, you take inverse tangent of 3 over 1, right? So inverse tangent of 3 over 1, basically, right? Or, if, I don't want to call you guys stupid, but if you're stupid like I am, my first thought was, oh, let me find this angle right here and then subtract 90 from it. Like, you could do that as well, but that's just like unnecessary. It's like more work. Because you would have done inverse tangent of 1 over 3, right? 1 over 3. You got this angle, and then we know that these two angles combined would give us a 90-degree angle. So you would have done like 90 degrees minus whatever this ends up being, the inverse tangent of 1 over 3. So that's just me trying to make things more complex. So this wouldn't be the 0 quite yet. So the 0 would have been here. So these two angles would be equal to each other. Yeah, because it's like two parallel lines. I loved most things about geometry, like just the concepts, but not the proofs. Proofs can go to hell. Anyway. So that's B, right? What is C? Yeah, facts. Proofs can go to hell. Straight to hell. I would get points off for not saying, like, if this, then that. That's just goofy. It's not like, I don't know. Anyway. Part C says find the net force, magnitude, and direction on Q3. On Q3. For the direction, give the angle to the x-axis. Man, these are some filthy problems to do in 20 minutes. I ain't gonna lie, like, this is kind of long to do in 20 minutes. Like, factoring in, like, anxiety and all that. Like, biologically is not optimal. Anyway. So once again, this is force on Q3, right? So force net on Q3. What does this mean? What does this mean? How can we translate this again? Exactly. It's how Q3 reacts to, excellent. So it's how Q3 reacts to or feels relative to the effects of Q1 and Q2. So it's how Q3 reacts to Q1 and Q2. That is extremely well said. And so now we're just effectively just calculating out FQ1 on Q3 and FQ2 on Q3, right? So they already gave us Q1 on Q3, and they said that's 1.42 times 10 to the negative 5 newtons, right? Now we need to figure out what's force of Q2 on Q3, right? So force Q2 on Q3, right? And this is KQ1 Q2 over R squared, right? That's the electrostatic force equation that we're using. K is our 9 times 10 to the 9th. Q1 I guess it wouldn't be Q1, my bad. It would be Q2 and Q3, right? And keep in mind that if you look at the equation sheet, once again, if you look at your equation sheet, you'll see that Q1 and Q2, or Q2 and Q3 in this case, they're taking the absolute value of each one and multiplying them together, right? So we don't care about the fact that one is positive, one's negative. We just multiply the absolute value together, right? So Q2 was 5 nanocoulombs. So that's 5 times 10 to the negative 9 coulombs. And then Q3 was what? Is negative 2 nanocoulombs, right? So we just plug in 2 times 10 to the negative 9 coulombs. We don't care about the negative sign. We make it absolute value. And then you divide by R squared, right? The distance between them, the R, right? Well, how can we figure out the R? How can we figure out the R here? And what is the R actually? Let me draw this out here. So this is Q2, Q3. This is this is that. This is 3 centimeters. This is 1 centimeter. So how can we figure out R? And actually, what even is R right here in this case? So excellent. We figure out R using Pythagorean theorem. And so r would just be the direct distance between Q2 and Q3 on that axis right here. That's your r. So you could either do 3 centimeters squared plus 1 centimeter squared, take the square root of that, and then convert your answer into meters, or you could convert to meters first and then add up. So you could do like 0.03 meters squared plus 0.01 meters squared, and then take the square root of that, and then you got your r, right? You could do either way. And here's like a quick tip as well, right? Since this is r squared at the bottom, there, man, you're always like ahead of the game. Exactly, right? So you don't even have to take the square root in this case, because you know that r squared is equal to 3 centimeters squared plus 1 centimeter squared, or 0.03 squared plus 0.01 squared. Yeah, we're on the same wavelength. So effectively, you could have, instead of having to take the square root and then squaring the square root again, you could have just kept this and just plug it in here, right? But obviously you have to have this in meters. So it'd be like 0.03 meters squared plus 0.01 meters squared, right? And then you just add them up together, and that's your r squared at the bottom. Don't like take this answer and then square it. No, this is your r squared, right? That's if you want to like hack the system and do things a lot quicker. But yeah, that's how you figure out Q2 on Q3. Now we're not done yet, right? Because we want to figure out the net force. So you might be thinking, well, F net, right? Well, there's F Q1 on Q3 and F Q2 on Q3. So can I just like add them together or subtract them or whatever? Well, you can't. Why? Because you have X and Y components to each one. So really, F net is equal to F net X squared plus F net Y squared, and then you take the square root of that, right? Well, what is F net X? Well, F net X will be made up of F Q1 on Q3X, and then either added or subtracted to F Q2 on Q3X. So the X components of both, and then same thing for the Y, right? F Q1 on Q3Y plus or minus, we don't know yet, F Q2 on Q3Y, right? So we already figured out F Q1 on Q3 X and Y. We figured these out from part A. So we just have to figure out what these are, right? We already figured out the angle from part B, right? We figured out the angle from part B. So we know here that for FQ2 on Q3X, right? So I'm going to say FQ2 Q3X. That's going to be equal to FQ2 Q3 times what? Cosine, my bad. Cosine of that angle phi, right? And that angle is like 71 degrees or 72 degrees or something like that, right? So cosine 72. FQ2 Q3 cosine 72 is going to give us that X component, right? And then FQ2 Q3Y, we can figure that out by taking the force and then multiplying by sine of that 72 degree angle, right? So that gives us the X and Y components there, right? Now the important thing is to understand that, once again, this is all dealing with positive, right? What other equation or what other concept other than electrostatic force that we mentioned and played around with a lot earlier uses only magnitudes, at least when you're calculating the initial value? So like in the equation for electrostatic force, we're using magnitudes. What other equation or what other concept did we play around with earlier also uses only absolute value, at least when you're initially calculating the value? Yeah, I mean, like, Coulomb's law is the electrostatic force equation, right? F equals Q1, KQ1, Q2 over R squared. I'm just saying, what other equation and what other concept have we talked about before that only uses absolute value in its equation for the charges? So, like, F equals K, Q1, Q2, and they're taking the absolute value of the charges divided by R squared. What other, exactly, finding the electric field, right? Electric field is K, absolute value of Q over R, or R, right? Just R, right? Or is it R squared as well? I can't remember. Hold up. Let me double check. It is R squared. Yeah. It is R squared. Yep. So you can see here that we're only calculating positive values, only magnitudes, only absolute values up to this point. Now, what did I say about electric fields? When do we throw in a sign? When do we start figuring out the signs of things? Whether it's positive or negative, actually. So, right, when it reacts to the charges, okay. And so it would just be the direction of, like, the movement of the charge based on how it reacts to other charges, right? So excellent. So now we have our f net x, f net y. We can complete those two equations. So f net x, and that would be equal to what? So q1 on q3x. So q1 on q3x. All right, let's look at that first. Q1, Q3, and Q2, right? So we want to figure out the net force on Q3, right? Q3, they said it was negative. Q1, they said it was positive, and Q2 was positive. How does Q3 react to Q1? What will Q3 to Q1 do? Exactly, it'll move to Q1 this way because it's attracted to it. How would Q3 react to Q2? So what is the force of Q2 on Q3? How would it react to Q2? Same thing, also moves towards it, right? Now you see here, what are the x and y components of this first force right here? FQ1 on Q3. Give me, like, positive, negative, y-axis, x-axis notation. Like, are the x components going to be, yes, positive, yeah, no, you're right, positive y-axis and positive x-axis, right? So positive x-axis, positive y-axis, right? How about Q1, or Q2 on Q3, I mean? So negative y, and then another positive x, right? So given now, what do I want to say? So, actually, you know what? I'm going to wait here. So we see here that, yeah, we see here that Q1 and Q3 has a positive y-axis component, negative y-axis component for Q2 on Q3, and then positive x for Q1 and Q3, and positive x as well for Q2 on Q3, right? So Q2 is effectively kind of like pulling Q3 downwards to it, and is going to be opposing Q1 pulling Q3 upwards to it, right? But both of those charges, Q1 and Q2, are working together essentially to pull Q3 to the right, right? So we want to figure out the F net x from the x components of both of these forces, right? So F net x, FQ1 on Q3 is going to be positive, and we're going to add that to FQ2 on Q3. Both of them are positive. We have this positive sign in the middle, positive sign here as well, right? And we just add them up. Perfect, right? How about F net y? F net y, we have FQ1 on Q3. Let's add x's here as well. FQ1 on Q3 y, and that was positive because it's the positive y-axis. But then we have minus FQ2 on Q3 y, right? Because it's in the negative y-axis, right? And when you plug in these values, you should get your F net x, and you should get your F net y. And then from this, F net would simply be equal to the square root of F net x squared plus F net y squared. Does that make sense for your F net? I think I might have forgotten a step here. Or no, I did. I'm good. Never mind. I thought we didn't figure out the x components for some reason, but we already did. That's why we would be using the equation at this point. So, but yeah, does that make sense as to how to figure out x and y components of these forces, how to draw the forces, how to draw the electric field lines, when to like have absolute value, when to throw in signs and stuff like that? Does that all like make more sense now? Because what I've explained here is like either for electrostatic forces or electric fields is going to be pretty much the same between them. You're always drawing things relative to how the charges would react to other charges around them. And then x and y components is just a matter of like doing your trig identities and stuff. And your radius is always the direct distance between two charges. Is this making more sense now as a whole? Okay, I'm hoping so. And Matthew, I think you were the one who actually asked this at the beginning, so I should be asking you directly as well. Like, is this all making more sense now? Okay. Mm-hmm. So for that type of question, like I said, you would have to imagine that that point is a positive test charge, like pretend it is a positive test charge, and then draw the lines in a way as to how that positive test charge, if it were there, how it would react, right? So if I had that, like I said, if I had like points A, B, and then it's like C off here, right? If this was a positive charge, this was a negative charge, and they're asking what's the electric field at C or what's the electrostatic force at C or something, right? Then they haven't specified what C is, but I can assume by convention that it's a positive test charge. So directly between C and A, Matthew, directly between C and A, how would C react to A? You can kind of like give me a rough direction. Yep, up and to the right, exactly. So we're imagining that this is positive. So positive repels positive. So it would move up and to the right along that axis, right? So you kind of like draw a line between those points, and then you draw your electric field vector or your force vector, right? How about for B? How would B move? Or how would C react to B? Exactly, down and to the right. So it's along that axis, down and to the right, because it's attracted to it. And we're assuming or pretending that there's a positive test charge there. So if they just say point, know that it's basically we're drawing things as if there was a positive test charge there. And Shireen, they will absolutely ask a question like this, to be honest. I don't know if it's gonna be like the exact same way, but you're definitely gonna have to be calculating like forces and vectors and stuff like that. It like whatever you guys have been seeing on the practice exams, more or less like the distribution of topics and what you're gonna see is pretty much almost the exact same as the actual thing. So that first practice exam, the first extra practice exam that I went over on Sunday night, that was my real exam that I took. So, I mean, um, you liked my exam? I liked my exam too. Oh, the one we did yesterday, that wasn't actually my exam. That one was the practice exam that I got. So, yeah. I mean, with this vector stuff, it just takes a little bit of practice to be able to figure out like the direction. But oh, you hated the yesterday's exam. Okay, so you liked my exam and you hated the yesterday's exam. Yeah. Makes sense. Gotcha. Yeah. Generally though, in my opinion at least, like usually the actual exam is slightly easier than the practice exam. At least my experience so far. But I mean, like I don't know, just and you can just be honest, like have I made any of this vector electric field stuff easier to understand, or is this just difficult still? Okay. I mean, I don't know who everyone is, but like I mean, I can't really yeah, I mean I'm inherently biased anyway because of this, but I'm not going by myself only, but I'm going by what my friends talked about and told me about their feelings about the exams when I took it as a student. But everyone felt that the exams got progressively easier over time. Um, but I don't know. That's just, I guess it just kind of depends from class to class, probably. But we all felt that even the third exam, like the third unit, had some just dumb and kind of tough topics. But um, that exam was probably easier than the second exam as well. So, yeah. But, yeah, I mean, I don't know what to say for this second exam stuff. Anyway, um, yeah, I mean, like, they're not gonna throw in, like, any crazy circuits, any crazy, like, loop rule stuff. Um, I doubt, like, okay, let me see here. Yeah, I mean, really, probably the toughest stuff is just the electric field and vector stuff. But hopefully, just by like doing a little bit more practice, maybe rewatching parts of the videos that I've explained this stuff with, um, that you'll be able to solidify it in the next like 24 hours, I guess. Um, but yeah. So, okay, it's 7 p.m. All right, so we got like, well, I want to make sure I don't overstep time anyway, because I mean, it's an open session, so I probably just ended on time this time. So, what is it? I just want to figure out when sunsets. Okay, 7:21. Right, cool. Yeah, so I'll probably just end it right at 7:15. So, any other questions about any of this stuff? Um, do you guys want to do another like electric field vector type problem? Do you want to do something else? What's the move? Um, Also keep in mind, like, if you go to my slides on Google Drive, set, like, I picked out a couple of different problems that I thought were the most important and the most helpful from the written, the online, and the practice problems. Not the practice problems, the reading, I mean. So the written, online, and the reading, I picked out the problems that I felt were the most important, and I added them at the end of the slides so you guys would know, like, which problems would be the best to kind of do. So, yeah. I think for this electric field stuff, if you look at the book problems, they are extremely good um, for getting practice about this vector stuff. So, new number 5 and number 6 from here's practice exam. Let me take a look at that real quick. Mahir's practice exam is just the one that you guys were given, so it's just your original practice exam, which in my Google Drive, that would just be the one labeled practice exam. So number 5. Yeah, 5 would be kind of long. And 6 as well. I wish we... Well, hold up. How are these short... Oh, no, these are long problems. Okay, so I guess, yeah. So I'm here to go over those then. I was about to say, like, I thought they were short problems for a second. Okay. So what I'll do, I can probably go over them really quickly and just kind of, like, outline how to think about them. But maybe not just go through, like, all of the math. Does that sound good? I'll try my best. All right. We might only be able to get through 5, but we'll see. So, let's practice exam. And then 5. Okay. So it says draw the electric field vector at point P and determine its x and y components, right? And we have Q1 is equal to -3 nanocoulombs. Okay. So kind of what I was talking about earlier. So point P, what should we assume this to be? What is point P in order to be able to draw the electric field lines stuff properly? Our test charge, right? Excellent. Right, so that would be what type of test charge, though? By convention. Positive, exactly, right? So we want to draw or pretend that the charge there is positive, and then we want to draw our electric field lines in a way that shows how that positive charge would react, right? So if we have that negative charge, negative charge there in the middle, positive charge over here, then how would we draw our electric field line vector? Wait, can you say that again? So we're looking at point P, right? This is point P, and we're drawing our electric field line in a way that shows that how point P would react to Q1, where Q1 is negative. So positive would be moving to the negative charge, right? So it wouldn't be southeast, right? It would be northwest. And the reason why is that we're drawing these lines not from the charge to the point, but from the point to the charge. We're always drawing it from the point to the charge because we want to see how the point will react to the charge. So it'll be this way, that way, right? So this will have an x component, it'll have a y component, right? And so we know that the electric field is only dependent on the charge around that point, or the charges around that point, and not the actual point itself. So if they told us that this point was positive 6 nanocoulombs, we don't care. We're only caring about the other charges around it, right? So we would do K, absolute value of Q divided by R squared, right? So we just plug in K. Our Q would be that Q1 value, and then your R would simply just be the direct distance between the Q and the point, right? And they told us that this vertical distance was 3 centimeters and this horizontal distance was 3 centimeters and 4 centimeters, my bad, right? And so you can use Pythagorean theorem to figure out then the direct distance, which should be 5, right? So 5 centimeters should be that direct distance, and that's what you plug in for your R. But make sure that it's in meters, obviously. And then once you have your electric field, that's your electric field magnitude, and we want to figure out the x and y components. So what can we do to figure out x and y components? How can we figure out x and y components of an electric field? Okay, yep, excellent. So we take the inverse tangent, and specifically the inverse tangent of the two distances, right? So we take like inverse tangent of 3 over 4 to get this angle, right? So inverse tangent of 3 over 4 will give us the angle theta. And then we do e cosine theta, for example, to get ex, and then e sine theta to get ey, right? So it's opposite over hypotenuse, that's your sine, and that gives you ey, and adjacent over hypotenuse, and that gives you your cosine, and that gives you your ex. So that's part A, right? Part B, determine the x and y components of the net electric field at point P, where they've added now a Q2, right? So here's Q1, that was negative. Here's Q2, that was negative. Here's point P, right? And we're, once again, if it's just a point, we're assuming that it's a positive test charge, right? And the y distance is 3 centimeters, and the x distance is 4 centimeters here, right? So, once again, how are we going to be... We already, essentially, like, we figured what this is already, right? We figured the electric field here. What's the electric field that point P is feeling from Q2? How would we draw it? Moves up, right? Because P, we're assuming it's a positive test charge, so it would be attracted to the negative. So it would just move upwards, right? Is there a x component? Is there an x component to the electric field of Q2 on P? No, just y, right? So if I want to find E net, right? Well, it's made up of E net x squared plus E net y squared, and then we take the square root, right? So what is E net x going to be made up of? Zero? Wait, hold up. What? Yeah, just Q1, right? So just the electric field from Q1, right? So just E1x, basically. And then E net y, right, would be your E1y plus your E2y, right? And why are we adding them up? Why are we adding up E1y and E2y? Okay. Why don't we subtract them? Excellent. Well, what about this? Do you notice anything wrong about this? Exactly. So this is along the negative x-axis, so it should be negative. Perfect. Negative E1x, right? Keep in mind that you're calculating your electric fields and your electrostatic forces just by using the magnitudes of everything, and then you add in your directions based on, like, if it's positive x-axis, positive y-axis, negative x-axis, negative y-axis. So that's it, right? That's your net x and net y, and then you can just follow this and calculate net electric field, right? Yeah, go ahead. Yeah, this is the practice exam that you guys got on Blackboard. Mm-hmm. And then C is asking what must be the magnitude and direction of the electric field created by Q at point P, right? And they said there is a different charge placed shown such that the net electric field at point P points to the left. Okay, interesting. So they kept Q1, which is negative. They kept point P right here, right? And they removed Q2. And instead of Q2, they just gave us a random Q, right? We're not sure what this Q is, if it's positive or negative. But they want the net electric field to be to the left, this way, right? Well, we said that P feels an electric field from Q1 that goes up and to the left, like this, right? And this has a x component and a y component, right? So if we wanted only for the electric field to be to the left, what do we need to do? Don't even like talk to me about what Q's charge should be and stuff like that. Like what should be happening here in order for E1x to be the only component? Yep, no problem.
Test charge should be moved so it's only like horizontal to Q1.
One sec here. So my earbud died, so I gotta switch out the other one. One sec. Okay, can you guys hear me? Yeah, no, can you guys hear me now? Okay. Okay, what did you say about the charge again, or about the component? You could move the test charge, right? But we're concerned about, remember, we're trying to figure out what the charge should be at Q here, right? So, like, essentially, yeah, you could move it to this point, and then you would only have an x component. But if you have this y component, right? So it's like we're asking how can we get rid of this y component, basically. Yeah, it has everything to do with the charge on Q. So if it was negative, and we're assuming that this test charge is positive, how would it react? Right? So then we'd have a double y component. Exactly. Exactly. So if it's positive, yep, exactly, it gets repelled, and so it moves downwards like this. So this is E2y, and so E2y should cancel out E1y. But we just have to find out what the charge of Q is to where that the electric field generated by it would cancel it out. Does that make sense? So effectively, you're just saying, okay, E1y is now equal to K Q2 over R squared. Does that make sense? Because you want this electric field generated by Q1, and the y component of it at least, be equal to the electric field generated by Q2. Or at least, hold up, maybe did I do that incorrectly? Oh, my bad. They're not asking for the charge on Q. My bad, my bad, my bad. They're not asking for the charge on Q. They're asking you just for the electric field that's generated by Q. And so the electric field generated by Q would just be, like, EQ would be equal to E1y, but downwards. So the absolute value of that would be that, I think it's like 6,000 something newtons per coulomb. And then it would be directed downwards along the negative y-axis. Yeah, 6,480. So the absolute value, the magnitude of the electric field would be 6,480. So it would be exactly the same as E1y, but directed downwards so that it cancels out E1y. Does that make sense? Yep. So they're asking for the electric field generated by Q, and it has to be equal and opposite to the electric field, the y component of the electric field generated by Q1. So E1y has to equal EQ, but the absolute value of it. And then EQ should just be, directed downwards. So yeah, basically, Matthew, just like negative E1y, basically. Does that make sense for everyone? And then D is actually where they're asking about the charge, right? D is where they're asking about the charge here. So yeah, you would set E1y equal to K Q over R squared, and then you're basically just figuring out the Q. And then the R that we're looking for here, right, would just be the And this is actually, I mean, you don't even have to say E1Y. You can actually just say EQ here. And then the R would just be the distance between point P and the Q, which is 3 centimeters. Does that make sense? Okay. So that, I believe, is all of problem 5, and it is 7:15 now, so I got done just on time for that problem to be done. Yeah, so I'm probably just gonna end the recording on this note, but give me 1 second here. I gotta tell you some things after I end the recording, but that's it for those who are gonna be watching online. And yeah, so this was just an open session where people just came in and asked questions, and